Good morning, everybody. Today, as a part in continuation with what we have learned in unit number 4 from the KTU syllabus of engineering mechanics, let us continue with work energy, impulse, momentum. These are four terms and four different terms. Obviously, they are interrelated to each other, and you need to understand how they function and what are their significances and how do we actually utilize these concepts in solving different problems related to mechanics. So, as we have already discussed about some previous topics like what is mechanics, what is statics, what is dynamics, what is kinematics, and the basic laws of motion and their and how they have been used in the normal form, in the numerical form, as well as in the differential form. So let us understand some basic terms. Work done is force into displacement. So force is a push or pull acting on the body, and displacement is the amount of transfer or in meters that has taken place for a body due to an applied force. The unit is Newton meter, obviously, and 1 Newton meter can also be said as 1 joule. Now, power is work done per unit time. So it is Newton meter per second. It can also be called as joule per second, and it is represented as watt. Now, coming to forms of energy, these are two basic common forms of energy. Uh, One is potential energy. This energy is by virtue of its location, where it has been placed, and the height of the body tells you about the net energy stored inside it. So potential energy is given by mgh. Now, if you talk about kinetic energy is represented by half mv square. It is the energy possessed by a body by virtue of its velocity. Now, if the body is rotating with a certain angular velocity omega, then the kinetic energy due to rotation is given by half I omega square. So it is similar to half mv square. Now let us take a small numerical. Uh, this is a block, 10 kg block, which has been placed on an inclined plane. The inclined plane is at an angle of 30 degree. The coefficient of friction between the inclined plane and the block is 0.2, and a force of 160 Newton, which is acting at an angle 10 degree, is acted upon the body, and the net effect of the load is to pull this up. So if you draw the free body diagram, means either you can take it on a flat plane and then rotate, as because it has gone in anti-clockwise direction 30 degree. If you rotate this mass by 30 degree in clockwise direction, it becomes as if it has been located on a flat plane. So then you can draw the free body diagram. If you draw the free body diagram, there are two ways of doing it. Mg acts perfectly vertically downwards, and the forces are managed accordingly. And the next type of doing it is you incline the weight itself and manage the forces accordingly. So if you draw the free body diagram, R is the reaction offered by the surface. Mu R is opposite to the direction of possible motion. 160 degree, it is acting at an angle of 10 degree. This 10 has been multiplied by 9.81 because this is 10 kg and the other force has been mentioned in Newton. So if you resolve this force system, coplanar concurrent force system vertically, as because it is in equilibrium, so you have two equations of static equilibrium for a coplanar concurrent force system. So if you resolve it vertically, you have 98.1 sine 240. I am taking outward acting forces as positive, and the angles are measured moving in clockwise direction, in anti-clockwise direction from the positive x-axis. So if you resolve it, you get the value of R, the normal reaction as 58.8. Now, if you resolve it in the direction of motion means horizontally. If you resolve it horizontally, you get the total work, you 0.2 into 58.8. This is mu r. And this 98.8 cos 2 for 50. 98.8 is this one, 98.1 mg. And 160 cos 10, 160 is given here, 10. So if you add up all the forces in the direction of motion, you get a net force of 140.8. Okay, so 140.8 is the net work done. Uh, Let us we are assuming that the distance traveled is 1 meter. So work done is 140.8 joule or 140.8 Newton meter. So this is how this problem has been solved. So let us take another problem. This is where a gun weighing 300 kilonewton fires a 5 kilonewton projectile with a velocity of 300 meters per second. With what velocity will the coil recoil? If the coil is overcome by an average force of 600 kilonewton, how far will the gun go in reverse direction? How long will it take? Now, in this problem, projectile is been written, but there is no application of projectile because we are not studying the motion of a body. We are studying the recoil velocity of a gun. So if a gun is used to fire a shot, obviously it will have certain recoil velocity, and the purpose is to find out the recoil velocity. The recoil velocity will be calculated by law of conservation of momentum. Now, momentum is mass into velocity. So, law of conservation of momentum says that the momentum uh, before any action will be equal to the momentum after any action. So, momentum, the net momentum is conserved. Okay, so the weight of the gun is given as 300 kilonewton, weight of the projectile is 5 kilonewton. The velocity is 300 meters per second. So 300 weight of the gun, kilonewton, multiplied by velocity is equal to 5 is the weight of the projectile, means the weight of the bullet, and it is fired at 300 meters per second. So this V comes out to be 5 meters per second. So the recoil velocity by conservation of momentum comes out to be 5 meters per second. Now, with this velocity, let us calculate the distance traveled. So, distance traveled is minus 600 into S. Okay, minus 600 means overcome by an average force of 600 kilo is equal to U0 minus half AT square. So, now here uh, half gt square, so 300 divided by 9.81 multiplied by s square. So s comes out to be 0.637 meters. So 0.637 meters is the distance traveled by the gun without any resistance in the backward direction due to the firing of the bullet. Now rate of change of momentum is equal to applied force. Okay, so why rate of change of momentum is equal to applied force? M, if you take out common, V minus U by T. So V minus U by T is acceleration. So mass into acceleration is the applied force. So 600 into 10 to the power 3 is equal to, this is final 300 minus initial is 0, T into 9.81. So T time taken is 0.225 second, and this 0.225 seconds is the total time in which the recoil takes place, or the distance that has to be traveled, which has been calculated earlier as 0.637 meters is been done. So this is how you solve certain problems in using impulse, momentum, and work done. Now, let us start with the next topic, and that is D'Alembert's principle. So D'Alembert's principle is the last topic that is covered as a part of your syllabus. Now, as we know that there are two possible types of systems that are mentioned in your syllabus. One is a coplanar concurrent force system. In a coplanar concurrent force system, you have two equations of static equilibrium. Sum of all forces in horizontal direction is equal to 0, and sum of all forces in vertical direction is equal to 0. Whereas If you have a coplanar non-concurrent force system, you have three equations of static equilibrium where sigma fx or sum of all forces in horizontal direction, sum of all forces in vertical direction, and sum of all moments taken about any point uh, is equal to 0. So this all we have gone through it. Now coming to Newton's second law. Newton's second law says that force is equal to mass into acceleration. So if we take it, if we remodify this statement, then F minus ma is equal to 0. So D'Alembert was the first to introduce that these equations of that dynamic equilibrium can also be established by introducing inertia force, because m into a is called as your inertia force, and this inertia force forms a part of the dynamic equilibrium, and this can be introduced, and this always acts in a direction opposite to the direction of possible motion. Likewise, you must have seen in when we were understanding friction, frictional force acts opposite to the direction of possible motion. Similarly, if you are try to understand dynamic equilibrium is governed by inertia force, and inertia force always acts opposite to the direction of possible motion. So this is the statement of D'Alembert's principle. Now, coming to some generalized cases of D'Alembert's principle. First is a motion of a lift. This is something very common. So in motion of a lift, what we see that a lift has only two possible motions. Either it can go up or it can come down. So let us say that when the lift is going up, whether it is going up or down, there are two components which are always fixed. One is the tension in the wire, which is supporting the lift, denoted by T. Okay. And the next one is mg, the mass of the lift. Mg is the total weight of the lift, and this may or may not include the weight of the person. So if in a numerical, if the mass of the person is also mentioned, this mg will be the sum of the weight of the lift plus the weight of the man standing in it. Okay, so this mg is always the total weight of the lift, including the passengers inside. If there is no mention about the passengers, do not try to add any other component into it. There will be a mass of the lift. This mass has to be multiplied by g, gets converted into mg, which is your weight of the lift. Now, there are two possible motions. First, let us see that if the lift is going upward. If the lift is going upward, by D'Alembert's principle of dynamic equilibrium, the inertia force will be acting opposite to the direction of possible motion. So ma is denoted in the downward direction. So by D'Alembert's principle of dynamic equilibrium, if you write down the equation for this, then you can see that the opposite T is in upward direction. Let us say that upward directions represent positive y-axis. So they have been taken as positive. mg is in negative y direction. So this is mg, and ma is the inertia force. This is also in negative direction. So this is a single equation out of which you can find out any maximum one number of unknowns. So whatever is given, you just need to put down the values. Whatever is unknown, only one unknown can be found out. If you look at the terms here, there are three terms, T, M, and A, because G is something which is constant, 9.81 meter per second square. So G is known to you. So you have three terms, T, M, and A. Out of these three, if any two are known to you, you can obviously find out the third component. Now, let us see the second case. The second case says that if the lift is moving downward, then what happens? Tension remains in its usual direction. Mg, the total weight, remains in its usual direction. But by D'Alembert's principle, Ma, the inertia force, acts in the opposite direction of the motion. So again, if you write down the equations of dynamic equilibrium, this comes out to be T minus mg plus Ma. So again, you have three possible variables here. Out of these three possible variables, if any two are given to you, you can obviously find out the third one. So we'll be now taking certain numericals, and in those numericals, I'll try to make you understand how they are solved. what are the concepts underlying them, and what are the various factors that you need to keep in mind. So, coming to the first numerical, here, look, in the case of motion of a lift, it is very clear that there will be only two possible motions, perfectly vertically moving upwards or perfectly vertically moving downwards. So obviously, there are no certain complications in solving problems of those types. Let us take a few difficult ones. Here you can see that you have an inclined plane. In this inclined plane, you have a 10 kg block kept here. You have a 20 kg block kept here. Okay, it is acting over a frictionless pulley, and you are supposed to find out the velocity of the system after 3 seconds. So obviously, if this pulley is frictionless, the velocity at which 20 kg block moves down, that same velocity will be acted upon on this 10 kg block while moving up the inclined plane. So if you find out the velocity of any one, obviously, if this pulley is frictionless, the same velocity will be transferred to the other body. So here what we are doing is, let us take this into two systems. So taking this 20 kg system, if you take this 20 kg system and draw the free body diagram of it, 20 kg system, mg is acting downwards, tension is always acting upwards. This block is heavier than this 10 kg block, so this will move down. So the direction of motion is also confined or fixed. This direction of motion will not be mentioned in your questions. So obviously, by looking at the diagram, you have to predict which direction the body is supposed to move or will be moving. So the direction of motion is somewhere down here. So by D'Alembert's principle, MA will be acting, or the inertia force will be acting upwards. So if you write down the equation for static equilibrium of this case, then you have T plus 20A, T plus 20A, M is 20, it is given here. So you need to understand where M is written as M and where M is written as mg. So these are certain mistakes that students generally make. So T plus MA is equal to mg. So T plus MA minus 20 G is equal to 0. So T becomes equal to 20 into 9.81 G, the value of G minus 28. Now considering the motion of the 10 kg body, if you look at the 10 kg body, it is placed on an inclined plane at an angle of 30 degree. Obviously, the direction of tension is predefined, because if this block is moving downward, the direction of tension is here. So here also the direction of tension will be in this direction. So the body tension is in this direction. So the direction of tension is predefined. The direction of motion of this 10 kg block is also predefined. It will move up the plane. If it is moving up the plane, MA, or the inertia force, will be acting on the other side of the motion. So if you try to solve it, if you write down the equation for this, the D'Alembert's equation, so you have T in this direction minus 10 into mg sine theta. M is here, M is 10, G is 9.81, and sine theta 10 into 9.81 sine theta minus MA. Why minus MA? T and MA are acting in opposite directions. So if T has been represented as positive, MA has been represented as negative. And this is according to the resolution of forces. So T now becomes equal to 98.1 sine 30 plus 10. Now you have two equations, 1 and 2. So let us equate 1 and 2. Both represent the tensions. So if you equate 1 and 2, you have this is equal to 98.1 sine 30 plus 10a. If you solve, you have a as the only variable that you need to solve. So a comes out to be 4.905 meter per second square. Now, if acceleration is known to you, the problem is you have to find out the velocity of the body 3 seconds after it is released from rest. So the time is 3. Acceleration is given. Rest means the initial velocity is 0. So the final velocity comes out to be 14.715 meters per second. So this is one numerical that you need to understand and see how it can be solved. So now let us take another numerical. Here also it is motion of connected bodies. You can see that there are two blocks of 2 kg and 6 kg represented by A and B acting over a frictionless pulley. Here also you need to find out the velocity of the system after 2 seconds. In the previous case, one block was perfectly vertical. Here both are acting at certain angles. So the only difference lies here that you need to resolve the forces properly. In the previous problem, resolution of one was very easy. Second one only had to be taken care of. Here, both are inclined at a certain angle. Okay, so if you look at the motion of block A, this is block A. By looking at the diagram, it is very well predictable that the 6 kg block will move down. So the direction of tension, the direction of motion, everything is predefined in the problem. It will not be given, or it will never be given as a part of the problem that the motion takes place in this direction. Just by looking at the diagram, you have to understand in which direction the motion is actually going to take place. So it is moving in this direction. A will move upwards, B will move downwards. So if you draw the free body diagram of this block A, tension is in this direction, motion is in this direction. So MA, the inertia force, is in opposite direction according to D'Alembert's principle of dynamic equilibrium. If you resolve this, you have T minus 2g sine 30, the angle is 30, T minus 2g means mg sine 30 minus 2a is equal to 0. So T becomes equal to 2g sine 30 plus 2a. Okay. Now for block B, similarly, if you go for block B, the tension is in this direction, the motion is in this direction. This is of 6 kg weight. So 6g mg sine 60 minus T is equal to 6a. So 6a and T both are in the same direction. So this can be represented as T plus 6a is equal to 6g. So T is equal to 6g sine 60 minus 6a. So this is your second equation. Okay. So now you have two equations, both represent the tension. So now let us equate 1 and 2. So you have 2g sine 30 plus 2a is equal to 6g sine 60 minus 6a. If you solve, you get the value of a as 5.145 meter per second square. You need to only find out acceleration because that is the only variable left in the problem. Now again you have to find out the velocity after 2 seconds of start because that is already given in the problem. That find velocity of the system after 2 seconds. So again, acceleration is known to you. Initial velocity is 0. Time is 2 seconds. You can find out the velocity after 2 seconds. The velocity of the system after 2 seconds is 10.29 meters per second. Now, in previous two problems, you can see that there has been no mention about frictional force acting between the surfaces. If you look at this problem, there is no mention about the friction which is present within the surfaces in contact or between the belt and the pulley. Now, let us take another problem where you will be having friction. So the coefficient here, you have a 20 kg block, you have a 80 kg block, they have been interconnected, and a force of 400 kilonewton has been applied to the 80 kg block. So one thing you need to clearly understand that the direction of motion will be in the right hand side direction. Another dimension that has been mentioned in the problem is the coefficient of friction between all surfaces is 0.3. Now you need to find out the acceleration of the masses. You need to find out the acceleration and the tension in the thread. So let us see how to solve this problem. So let A be the acceleration of the body. So one thing is very clear that MA for both the systems will be in the same direction that is opposite to the direction of motion. So as per D'Alembert's principle of dynamic equilibrium, the algebraic sum of all active forces acting on a system should be equal to 0. So the total inertia force is given by total forces is 80 plus 20. They are perfectly vertical, so you can simply add them. So 80 plus 20 MA. The total frictional force is mu mg. So total M is 80 plus 20 mu mg. So this is mu, the value of mu is 0.3. This is 100 into 9.81. It comes out to be 294.3. and this also acts in this direction, and inertia force also acts in this direction. Okay, so this situation is very clear now. Now, this is 400. So, by dynamic equilibrium, 400 minus 400 will be the tension in the string. So, 400 minus 100A minus 294.3 is equal to 0. So, you calculate the value of A as 1.057 meter per second square. Now, to determine the tension, because the other part of the problem is find the acceleration of the masses that you have found out as 1.057 and the tension in the thread. So to find out the tension in the thread, you can take any block. If you solve using any block, because now you are aware of the value of acceleration. So you can take any block for solving the problem. So let us take the 20 kg block. If you look at the 20 kg block, T acts in this direction, motion is in this direction, MA is in the opposite direction by D'Alembert's principle, and mu mg, the frictional force, is also in the opposite direction. So if you simply write down the equation for dynamic equilibrium, it comes out to be T minus Ma minus mu mg is equal to 0. So put down the value of M as 20, and you get T is equal to 80 Newton. If you would have taken the second block, then also you would have got the same answer. So these are some typical examples by help of which you can solve problems of dynamic equilibrium, and it will help you in understanding unit number 4 completely. So it is better that you take different numericals from different books, and you can solve them and understand them better. Thank you.